डॉक्टर बाबासाहेब आंबेडकर ओपन युनिव्हर्सिटी.
Namaste dear students, I Samda Rathod, Assistant Professor at School of Computer Science Department, welcome you all from our Chaitanya Studio at Dr. Babasaheb Ambedkar Open University. So, in today's session, we are going to learn about fundamentals of operating system and security. The block number 2, which is process management, which includes unit number 3, process scheduling. So let's start today's session. In last session, we have learned about round robin scheduling algorithm and priority scheduling. So today's agenda will be to learn about multi-level queue scheduling and thread scheduling and multiple processor scheduling. So let's start. This scheduling algorithm uses more than one queue and is used for situations in which processes can easily be classified into different groups. Here, no processes in the background queue could run except the foreground queues are empty. If a process entered the foreground queue while a process from the background queue is running, then the background queue processes will be preempted and the new process from the foreground queue gets the CPU, causing possible starvation for the background queue processes. To address this problem, time slice can be used between queues where each queue gets a certain portion of the CPU time, which it can then schedule among the various processes in its queue. So, a multi-level feedback scheduling algorithm is another implementation of multi-level queue where processes have the right to move between the several queues of the ready queue instead of being placed permanently into queues at arrival time based on their CPU burst properties. A process that uses too much CPU time is degraded to a lower priority queue, and a process that waits too long is upgraded to a higher priority queue. So now let's understand this algorithm by an example. Here you can see a MLFQ scheduler algorithm with three queues: Q0 with time quantum 8 milliseconds, Q1 with time quantum 16 milliseconds, and Q2 on FCFS basis, means first come first serve basis only when queues Q0 and Q1 are empty. So a new job enters Q0 is served by FCFS and receives 8 milliseconds. If not finished in 8 milliseconds, it is moved to Q1. At Q1, the job is again served by FCFS and receives 16 milliseconds. If it is not completed, then it is preempted and moved to another process, another queue, to Q2, where it is served in FCFS order with any CPU cycles left over from Q0 and Q1. Next, we will understand about thread scheduling. When several processes are available with several threads, scheduling differs as to whether the threads are user level or kernel level. So, if threads in a process are user level, the kernel operates as usual only on process since it is unaware of the threads, and the scheduler schedules the processes by giving them control of for a quantum. A thread scheduler inside a process will then use any of the scheduling algorithm discussed previously and picks a thread and grants the execution time. This is the this thread runs until it finishes its job or until the quantum time for the process ends, in which case the system scheduler takes the CPU and grants it to the another processes. When the first process is granted the CPU again, that the same thread resumes its execution and if it did not finish its execution earlier. So in this type of case, only the threads within the process are affected, and other processes in the system will run without being affected. If the threads in the process are of kernel level, the kernel operates on the thread and picks them to run by giving a fixed quantum uh, and forcibly suspend the thread if it exceeds the quantum allotted. So the scheduler does not consider from which process a thread is picked to run. Here the main difference between these two threads are implementations scheduling is performance, where the kernel level scheduling requires a full context switch, as every information related with a thread from one process must be maintained before a thread from another process get to execute, making the algorithm too slow. So in the next slide we will see that what is multiple process scheduling algorithm. So to increase the system's overall performance, numerous processor or cores are frequently used in modern computer systems. The operating system must be able to effectively schedule processes to execute on various processors, though in order to make the best use of these available resources, it involves processor to or core any other processes how long they should be permitted to run, while ensuring that all processes are fairly and appropriately prioritized. The objective here is to achieve efficient utilization of different processes available to the processors. Multiple processor system can be homogeneous. Multi-processor systems can be homogeneous means they are all same kind of CPU, and heterogeneous means various types of CPUs. So another approach here, let's consider a system with homogeneous or identical processors and discuss the different possible scheduling mechanisms. One scheduling possibility is to use asymmetric processing, where one of the processors entitled as master server and handle all scheduling, IO processing and all other systems activities, while the remaining other processors handle only user codes. Another approach here in multiprocessor system can be symmetric processing, where all processors have similar level and scheduling is done by each independently process. In a SMP system, each processor is comparable and has the same access to the memory and IO resources, means input out resources, while in the MP asymmetric architecture, one processor known as the master processor, and it has complete access to all of the system's resources, particularly memory and other I/O devices. Scheduling then proceeds by having the scheduler for each processor examine the ready queue and select processes to execute another processes. The ready queue can be separately maintained one by each processor, or commonly ready queue shared by all processors, where the first scenario could make one processor be idle with an empty queue, while another processor too busy with full ready queue. But if a common ready queue is used, all processes go into the one queue and are scheduled onto any available processor. So, in today's session, we have learned about multiprocessor scheduling, thread scheduling. So, in next session, we are going to learn about Unit 4, process synchronization and deadlock. Thank you for your attention. Please subscribe our YouTube channel BAOUGujarat.
स्वाध्यायः परमः